Okay, we're going to continue on here. We're in the middle of this example, I think. Perhaps. There it is. We've been obviously talking about titrations, and we talked about three different types of titration and titration curves. Again, a titration of a strong acid with a strong base, a titration of a weak acid with a strong base, and titration of a strong acid with a weak base. Remember that pretty much in all these titration curves, there's really four parts to the curve that we are interested in. We're interested in what happens at the very beginning before we start titration, before the equivalence point, the pH at the equivalence point, and then after the equivalence point that occurs. Again, depending on the type of titration that you have, you will get sort of different pHs at the equivalence point. So the equivalence point being the point where the moles of the acid equals the moles of the base. In a strong acid, strong base titration, because the salt that you have left over, which is really the only thing there, is a neutral salt. The pH should be around 7. Again, when we get into the weak acid, strong base titration, you will have, again, a salt at the equivalence point, and that salt came from a weak acid, which means it will act as a base and accept the H+ from water and will always produce hydroxide. So we do expect that titration to end up in a basic pH at the equivalence point. And lastly, when we have that strong acid, weak base titration, again, at the equivalence point, we have a salt that's left over, and that salt comes from a weak base, which means it will act as an acid and go through hydrolysis and actually donate the H+ over to water. That will produce H3O+, and again, we expect it to be acidic. So those three different types of titrations we talked about will have sort of a different pH at the equivalence point because of what is in it. All right, so we're into some problems here. I think we did through B, if I'm not mistaken. So I think we're on C. So let's take a look at C, which is actually the equivalence point in this titration. And let's go through it here. So part C, which is what's the pH at the equivalence point. And again, here we are doing 100 mils of 0.1 molar nitrous acid with, I think, 0.1 molar sodium hydroxide. Bless you. So as we talked about, when we're at the equivalence point, we will have basically equal moles. So we are not actually told the total volume here to reach the equivalence point. So there are a few different ways that we could get it. One way we could get it is because the reaction here, obviously, between our HNO2 and our sodium hydroxide is a 1-to-1 relationship when we write our balanced equation here. We can use M1 V1 equals M2 V2 to get it, again, because the relationship between these two are 1-to-1. In that case, basically, we will need 100 milliliters to reach the equivalence point, and you get that by obviously 0.1 times 100, which is what we're starting with, M1 and V1, divided by M2, which is also 0.1. Those guys cancel. 100 milliliters is basically what you need. So we'll get our moles here, and again, we do need to do an ice table in moles, and we'll have, starting with here, 0.01 moles of our HNO2. Again, another thing that we can figure out is, because it is the equivalence point, we know we should have the exact same number of moles of sodium hydroxide, which means we actually know the moles, we know the molarity. So again, another way that you can figure out the volume to reach the equivalence point is basically just use the molarity equation here and solve for volume, and you'll get 100 as well. This is going to be 0. Because we're at the equivalence point, you hopefully cannot pick a wrong number, because there's only one number to pick in this case, right? And we're going to do this. That's going to get us at equilibrium 0 and 0, 0.0100 moles. Any questions on the ice table here? Yeah. Now, the reason we do need to figure out, like we did earlier, the volume to reach the equivalence point is because at this point we do need to turn our moles back into molarity. So we need the total volume at this point. And in this case, we started with 100 and we needed 100 to get there. And that is 200 milliliters total volume. And again, that's what we need to convert back into molarity, which, as we talked about a number of times, is always the right move. Pretty much if you are doing an ice table here, you should really just convert back to molarity at the end. Now, we can look at what's happening here, and if we're not sure what's going on, we basically have just this guy left over, which is a salt. And in this case, what we always want to look at when we do have a salt is whether or not it will go through hydrolysis. And when we look at sodium nitrite, that is a sodium ion and a nitrite ion. This guy we do not have to worry about because it is group 1. This one definitely comes from our weak acid here. And that means that it will go through hydrolysis. So because it comes from this weak acid, it is a conjugate base, which means it will then go through a hydrolysis reaction where it will act as a base, which means it will accept the H plus because frankly, it does not have the ability to give the H plus. And that's going to get us where it came from. And that is going to produce hydroxide in this case, which is what we would expect in this type of titration, as it's a weak acid, strong base. That also should tell us we should end up with a basic pH when we're all said and done. In this case, we need a second ice table where basically we use the concentration of the salt that we got from the first ice table to continue on. This is going to be a regular table using molarity and X's. And again, this is why you do need molarity here to go into this table and not moles. We're going to end up here 0.05 minus X, X, and X. Questions on that so far? This is going to go into our K expression, which again is our products divided by our reactants. And this is a Ka, Kb. This should be a K, Kb. And again, that is what that also tells you, that you do need to be using a Kb value. Once again, in this problem, we're not given a Kb. We are given a Ka here, which is 4.5 times 10 to the minus 4. So the Ka is 4.5 times 10 to the minus 4. We need to use our Kw to swap that out. So our Kb in this case, 1 times 10 to the minus 14, which is our Kw value, divided by 4.5 times 10 to the minus 4. And that's going to get us here. Looks like 2.2 to the minus 11. At this point, we can put in here our x squared, our 0.05 minus x equals 2.2 times 10 to the minus 11. I think I'll swap over a page here. So we have x squared 0.05 minus x equals 2.2 times 10 to the minus 11. At this point, we can assume x is equal to 0. That's going to give us an x squared, a 0.05 equals 2.2 times 10 to the minus 11. We're obviously going to multiply and then square root it. And that is going to get us here. Looks like an x value with a lot of zeros there. So I'll do a little scientific notation like we're in chemistry class, maybe. We'll do 1.054 times 10 to the minus 6. We always want to check it, so we'll divide it by 0.05. We'll times it by 100, and the check is good. We're not even near 0.1%. So this x, we do also need to remember that when we do look at our ice table there, x in this case is actually the hydroxide concentration. Again, not the OH minus concentration. So that is equal to our hydroxide. That means it's going to allow us to get the POH minus the log of 1.054 times 10 to the minus 6. And that's going to get us a POH here. Maybe, there it is. 5.98. So again, if by some chance you thought that was the pH, it should not make sense to you because it should be basic. So we do need to subtract our 14 from that. So the pH in this case would be 14 minus 5.98. Going to get us an 8.02, which is basic and more like what we should expect to happen here at the equivalence point because of that salt going through hydrolysis. Any questions on that there? All right, so we got to the equivalence point in this titration. It's basic like we expect. Now we're going to do the last part here, which is what is the pH after we add 105 milliliters of the base. So we have 100 milliliters of our 0.1 molar nitrous acid, 105 milliliters of our 0.1 molar sodium hydroxide. And we're looking for the pH. So once again, obviously we've done the titration because we just did the equivalence point. So we should be past the equivalence point would be my guess. All right, so initially here, we are starting with this. We are adding this guy, and we'll get some moles here. So 0.1 times 0.1 again, 0.01 moles. We have 0.105 times 0.1, 0.0105 moles, and 0. Again, if you weren't sure where you were at, you can do a comparison. In this case, the moles that we're adding is greater than the moles we're starting with. So that definitely tells you you are after the equivalence point, as those guys, as we saw in the last example, should be equal to each other. Remember, at this point, there's that shift that occurs, and basically our acid in this case is our limiting reagent. Our excess reagents actually are sodium hydroxide. So we're going to go minus 0.01, minus 0.01, and plus 0.01 moles here. That's going to get us at equilibrium 0 and 0.0005 and 0.01. We want our total volume here so we can convert it back into molarity. So obviously here we started with 100 milliliters. We added 105. So we're at 205 milliliters total volume. We'll divide this by 0.205 liters. 0.205 liters here. Get a couple answers there. Looks like 0.00244 molar. And 0.01 divided by 0.205. Got 0.0488 molar. At this point, we have basically this guy left over and this guy left over. Again, hopefully you know that these guys are not related to each other. Again, they are not a buffer or anything like that. So we really have two things at this point in the titration like we would expect to have, and that is we have our salt here that can go through hydrolysis and act as a base. But we also have this guy, which is definitely a strong base. So we kind of have two base type situations happening. Out of the two, definitely our sodium hydroxide here is going to be a much stronger base and major contributor to the pH, as all it has to do is go in and it will break off into hydroxide. So remember, in this point in the titration, we ignore the contribution of the salt. And that means that in this case, we really do have the hydroxide concentration. And that could then get us our POH minus the log of 0.00244. And that will get us 261 minus our 14 to get to our pH here. 11.39, which is definitely basic and what we would expect to happen, as at this point we're just dumping basically base in there past the equivalence point. adding a lot of OH minus really quickly to the solution. And again, as we talked about, this is why we do see once we hit the equivalence point, usually that kind of big jump in pH as well, because you're adding a lot of OH minus really quickly to that solution. Question on that one there. All right, question on titrations. Clear, you need to be able to answer what the pH is and calculate it anywhere along any titration curve that we talked about. Are 400 points if I'm just really angry with you when I write the exam, right? Just give me 400 points along a titration and calculate it. Any questions on that there? All right, so last thing, I can't believe I just said that. Last thing we're going to talk about here in chapter 14 is acid-base indicators. And we sort of touched upon it as we've been going through. And acid-base indicators really work like weak acids. So indicators, which is what the INs kind of stands for here, is the indicator. It has a protonated form, which means it has a hydrogen on it. And it has a deprotonated form, which means it releases this hydrogen, much like an acid or a weak acid will do. And depending on the ratio of sort of the protonated form of the indicator to the deprotonated form of the indicator that's in the solution, as to which color will sort of predominate. As we talked about before, most acid-base indicators work over a pH range. And within that pH range, we usually see some type of color change that occurs. And not all indicators are equal in terms of sort of usage. So for example, here, as you can see here, crystal violet works at a much more acidic pH, like 0 to 2. And you go from kind of yellow to green to blue to really dark blue as you continue on in those sort of color changes. One obviously we're mostly familiar with is over here our phenolphthalein, which works again from about 8.3 to 10. And again, it is colorless at this point, and again, gradually sort of changes color to red or pink as the pH gets closer to that 10-9 marker there, basically, in that case. So what happens with phenolphthalein right before you get there, it is still this color at the end, right? So it's still colorless until you get there. And same thing with the rest of these, it's still that color basically all through there. And then you will see that color change basically extend. So the idea when you're kind of choosing an indicator is you do want an indicator that would actually change color near your equivalence point. So for example, the one that we just did, which was about a pH of 8 at the equivalence point, this would probably be a really terrible choice, as by the time you get to like a pH of 3, the color is already changed. You're not going to see any other color change is going to occur, and you will have no indication of, where you should stop your titration. That's the purpose of the indicator, right? It's to kind of tell you, hey, maybe you should stop at this point, right? Also, this guy here would be not a great choice either for that titration, as obviously the color has went. Something like phenolphthalein would be good, right? Again, we have that color change happening between 8 and 9. And again, that's why they yell at you to get the lightest color of pink, because that will put you near the equivalence point when you do that. So when you're choosing an indicator, you always want to choose one that you can see a distinct color change near the equivalence point to help you know you should stop your titration. So with that in mind, why don't you choose off the list here, which ones would be good indicators for this titration? What type of things you're dealing with. So this is obviously like the one we just did there. So we know this is a weak acid, this is a strong base. And that means when we think about the titration curve and the equivalence point, it should be basic in this case. And it's going to be basic based on what we saw earlier, because the salt that comes from it will act as a base and accept the H plus, and that's going to make here hydroxide, and we would expect it to be basic. So because of that, obviously this is probably not so great, that's not so great, that's not so great, that's not so great. That's not so great. Again, all these are going to have a distinct color change way before your equivalence point's going to happen, so that's not going to help you out at all. Although this one does get into the basic range a little bit, it's probably not far enough. The change for the color probably has already occurred at that point. So that leaves us really these bottom two here, which would be creosol red and phenolphthalein, which would be good choices for, this indicator to use. Now, you could, for example, do a theoretical calculation of your pH at the equivalence point based on your molarities and volumes that you're using. And you can really dial in maybe which one of the two might be better or worse to do. For example, obviously we hit an 8.0 or something like that. So maybe phenolphthalein might be a little bit better because that's starting where the color change should occur, as opposed to here where we're kind of almost to the end of it as well. Obviously, if we were doing something like the strong acid, weak base titration, you're going to be in the acidic range. So again, these guys would be much better sort of choice. And again, you could do that theoretical calculation and maybe choose one that's better than the other based on sort of your conditions. Any questions on indicators there? All right, I can't believe it, but chapter 14 is done. There it is. 92 weeks and chapter 14 is finally done. To chapter 15 on our downhill slide here of our roller coaster. So chapter 15, we're going to talk about some more equilibrium constant. We're going to talk about KSP. KSP is the solubility product. These are for things that are insoluble. And we're going to talk about KF, which is the formation constant. And this guy is for complex ions, basically. So let's talk a little bit about KSP first. Now, KSP and solubility, if you remember your solubility rules, maybe, yes, no, maybe make you remember the solubility rules. No, they just gave it to you. Yeah. So if you're not familiar with your solubility rules, things like nitrates are soluble in everything, chloride, bromide, iodine are soluble in everything except for silver, mercury, and lead. You may want to review them, although you probably could get away with it because there's a lot of ways to figure it out without it, but might be a good idea. All right, so when we talk about silver chloride here, which based on solubility rules is insoluble, one of the things that maybe they didn't teach you when you talked about solubility and solubility rules is even though, for example, the solubility chart or table tells you, for example, that when you put two things together, you should get a solid, there is a lot of factors that occur as to whether or not you'll actually see the solid form. Some of the things that can affect solubility we will talk about today. Things like are in this chapter, things like concentration, things like pH, things like common ion could have all effects on solubility. So when we look at something that's insoluble like silver chloride, even though something is technically labeled insoluble and will make a solid, it still has some degree of solubility. It will still break apart a little bit in solution, and it will actually set up an equilibrium like we see here. And because it will set up an equilibrium, we could write an equilibrium constant, and this is what is known as KSP, which is the solubility product. And we would do it like any other equilibrium constant, which is products divided by reactants. The one sort of exception, though, with KSP is this. Pretty much the equations for KSP reactions are always written like this, where solids on the left and really aqueous ions are on the right. And that means that pretty much when you write your KSP expression, it is typically just the products. And that's because the reactants are always solids in this case. And that's how you should always kind of write the reactions in most cases here, solids going into ions. So even though based on solubility rules, it tells us that silver chloride is going to make a solid and it will mostly make a solid, there will still be a little bit of it that will be able to break apart in solution and form just a tiny bit of ions that are floating around. We still do the exact same thing we normally do with K expressions, and that means that if you do have a coefficient, you still, again, take it into account here. So we obviously have a coefficient, we take it into account. We got coefficient on both of those, we still take it into account. Now, one of the things we could use KSP to help us understand is whether or not, for example, if we mix these ions together, would we actually expect a precipitate to form or not? And to help us sort of figure that out is we use a letter that we saw previously, which is Q. And remember, Q is the reaction quotient, and Q is calculated the same as K, right? So we calculate Q the exact same way as K. Remember, we saw it early on to help us determine whether or not a system was at equilibrium, and also help us determine if it wasn't at equilibrium, which way it needs to go to reach equilibrium. Now, if you calculate Q and you versus the KSP value and compare it to the KSP value, and the Q is less than the KSP value, you will have an unsaturated solution. And an unsaturated solution means that you could actually still get stuff to dissolve at that point. You should not expect any type of solid to form. Now, if you calculate Q and it actually equals to KSP, you technically at that point have a saturated solution. And if you remember the definition of a saturated solution, that is a solution where basically at that particular temperature, you've hit the maximum amount of solute that will dissolve in that solvent. So if you add any more at that point, it will not continue to dissolve. It basically will just kind of pile up. So that's the maximum amount that you can get to dissolve. You're pretty much at the tipping window of you're going to start to see a solid basically at that point. And if you calculate Q and it's greater than the KSP, you have what is referred to as a supersaturated solution, which means you have too much solid dissolved and it will come out of solution and you will see a precipitate form. Once again, if you just want to go opposite of where the Q arrow there is pointing, it will kind of tell you. So if you put your KSP on the right and the Q on the left, Q is less than KSP, it goes to the right. To the right are aqueous ions, no solid. It points to the right here on the bottom. Opposite is to the left. You get a solid in that point. So that's a good way if you want to kind of remember it that way. It will always go opposite sort of where the greater or less than sort of sign goes. Here are some KSP values that you'll find in the table in your book, which you might have to reference. And one of the things that you'll see in a KSP table, like I mentioned before, are really, really small values for KSP. And that is because this is an equilibrium constant for things that are mostly insoluble. And that means it's going to basically stay on the reactant side. And again, a small value of K means you're hanging out on the reactant side, right? You're not producing a lot of products in this particular case. And again, you can see some of them are quite small to the minus 47, minus 54. So these are typically really, really small values of K. Now, when we talk about KSP, we really talk a lot about solubility. And when we talk about solubility, there is kind of two types of solubility that we typically calculate. And one is known as the molar solubility. And the molar solubility is the number of moles there is dissolved in 1 liter of solution. It is, for all intents purposes, the molarity, basically, right? So that is moles per liter. So that's really the molarity, right? Then a lot of times we oftentimes like to know about solubility in sort of usable sort of units. And usable units for us is usually grams. So sometimes we'll look at the solubility in grams per liter. By the way, if I have moles per liter, which is the molarity, and I want to get to grams per liter, the thing that allows me to do that is the molar mass from the periodic table. Yeah, so the molar mass is what allows me to go from moles per liter to grams per liter. and also vice versa, going in the opposite direction as well. Now, you could also obviously have solubility given or asked for in any type of units, but these are again the two most common ones. When we talk about sort of KSP problems, there's really kind of two types of problems that we come across. And really, in one of the problems, you should always use an ice table. And the other problem, well, frankly, you should maybe still use an ice table, but you don't necessarily have to, but it's probably a good idea as well. So, one type of sort of KSP problem is you're asked to actually solve for what is the value of the KSP. So they don't give you the KSP, but they want you to solve it. And usually what they will give you is the solubility of the compound. And again, that could be in any unit. You want to get the molar solubility of the compound, you want to get the concentration of the ions, and then you could go into the KSP sort of expression and solve for it. The other sort of problem, which is very common, is they just give you the insoluble compound and they want you to figure out what is the solubility of it. And in that case, they will actually give you the KSP. So in this case, this is definitely an ice table situation, and really probably it's helpful to do an ice table there as well, but you don't have to do so. So let's take a look at one together, and we're going to talk about sort of how to go through it and what you need to do. So the solubility of silver phosphate, dramatic pause there. I'm not sure why it's so spaced out there. Put it back together a little bit. At 25 degrees is 1.6 times 10 to the minus 5. What is the KSP for silver phosphate? So this is a problem where you don't necessarily have to do an ice table, but it's really probably a good idea because there's a lot of places in these type of problems that people maybe second guess themselves in a sense because you may have to, for example, multiply something by 2 and also square it. And they go like, well, I squared it. I don't have to still multiply by 2. Or they multiply by 2, they forget to square it. So sometimes the ice table will sort of visually show you what you should do. So if we were going to do an ice table, we would start with our solid here on the left. And by the way, I know it's a solid because frankly, there's a KSP value. So we have a KSP value we're looking for. And because there's a KSP value, or not really, but we're looking for it, I know that's going to be insoluble. So this is going to break apart into 3 silver ions and a phosphate ion, basically. That is, by the way, going to give us a KSP of the concentration of silver. Once again, we do need to cube it because of the coefficient that's here times the phosphate. All right, so if we're going to do an ice table here with KSP, we actually do the table not super different, but a little bit different. So let's talk about some of the differences. First difference is not really a difference. It starts the same. We're going to go 0 and 0. We are going to probably ignore this side because it's a solid, so it's not in the equilibrium constant. So we don't have to worry about really the left-hand side here of the ice table. The change is normally we would go minuses to positives, and we still do that. Again, we just have nothing to put here because it's a solid. So we're going to go to the other side. And this is going to be plus 3. And we actually do use a different symbol here usually when we're doing this. And we use the symbol S instead of X. And what does the S stand for? S stands for the molar solubility. That is, again, basically the molarity is basically what it stands for. And here, this would be plus S. So once again, we basically just do like our X's, but it's very common to use S's here. We'll carry down like normal, gives us 3S and S in this case. Any questions on that there? Just like normal, we could go into our KSP expression. So that would get us basically the KSP is equal to 3S cubed times S. Now, normally, for example, if you did have the KSP, you would solve for S like a normal, like you would solve for X at that point, and you would get the molar solubility when you do solve for S. So if you did have the KSP given to you, you would do this ice table, and again, just solve for S like you would solve for X. At that point, you would have the molar solubility, and then you can figure out the what the grams per liter or molar solubility is. In this case, though, we don't have the KSP, so we can't solve for S, but we do have given to us the solubility of this guy in molarity, which means our S in this case is 1.6 times 10 to the minus 5 molar, as that is the molar solubility here. That means in this case, to find our KSP, we'll just plug that in. That is 3 times 1.6 times 10 to the minus 5. And again, we still need to cube it times 1.6 times 10 to the minus 5. So again, this is the benefit maybe of the ice table, even though you might not have to do that here, is you can still hopefully visually see you do need to multiply it by 3, and you do need to still cube it. So again, it's very common people will do one without the other. That's going to get us something. That's going to get us a KSP of 1.8 times 10 to the minus 18. Again, it's a K value, so no units or anything, just a number. Any questions on that one there? Okay, so let's take a look here at another one. So why don't you try this one? What is the solubility? Let's go in grams per liter of silver chloride. Okay, so let's take a look. So obviously silver chloride, we'll start with that. That should be AgCl. That is a solid for sure because we got a KSP. It is going to set up an equilibrium. We'll break apart a little bit into its ions in solution. Going to give us a KSP expression of silver times our chloride in this case. And obviously that equals our 1.6 times 10 to the minus 10. So in this case, when you're only given the KSP, it definitely is ice table territory. So we're going to go 0 and 0. Again, change going to be plus S and plus S. That will get us here at equilibrium, S and S. Once again, we're not really too concerned over here as that is a solid and not really in our equilibrium. This is going to go into our expression. That's going to get me basically S times S is equal to 1.6 times 10 to the minus 10. That's going to give me an S squared equals 1.6 times 10 to the minus 10. A little square root action on both sides there. Gonna get me 0.00001265 in this particular case. So that is essentially, we got there we'll call it 27 times 10. 1, 2, 3, 4, 5 minus 5. That is S. And in this case, a reminder that S does stand for the molar solubility of the whole thing. And that's basically our molarity at this point. That is, again, when you do solve for S, that is basically the molar solubility of the whole thing. It may or may not be the molarity of your concentration of your ions. In this particular case, it would actually be your concentration of your ions. Like our silver ion at equilibrium is also this number because that's what it equals, S. And so is our chloride is also this number because it equals S as well. And it's also the molar solubility of the whole thing. So at this point, we basically have 1.27 times 10 to the minus 5 moles per liter of silver chloride. We will need a little molar mass there from the periodic table, 107.9 plus 35.45. going to give us a molar mass of 143.4 grams per mole for silver chloride. Moles are going to cancel, and that's going to get us here 0.0018 grams per liter of silver chloride. First off, any questions on the calculation? Is that a lot of silver chloride that I could get to dissolve in a liter of solution? That is not. We basically could get to dissolve in a liter of solution 0.002 grams in 1,000 milliliters of water, which is why we consider something like silver chloride to be insoluble, because in 1,000 milliliters of water, you could only get 0.002 grams of it to dissolve. So it's definitely insoluble. Yeah. Any questions on it there? All right, let's try another one here then. What is the aluminum concentration in an aluminum hydroxide solution? KSP is 2 times 10 to the minus 32. So see what you come up with here. The KSP. So that's where we're going to start with our sort of equation and our dissociation here. Again, it's going to break apart into an aluminum ion, and we are going to get 3 hydroxide ions in this particular case. That's going to give us a KSP here of aluminum times hydroxide, and we do again need to cube it because of the coefficient. That will equal our 2 times 10 to the minus 32 in this case. So if we go through this here and do our table, we're going to have 0 and 0. Again, change here going to be plus S plus 3S. Again, at equilibrium here, S and 3S. Question on the table. We're going to go into our KSP expression here, and that's going to get us basically S times 3S, that again still needs to be cubed, equals 2 times 10 to the minus 32. That's going to get us a 27 S to the 4th equals 2 times 10 to the minus 32. Remember, you got to also cube the number, which is commonly missed by people. They just do like the S. So make sure you also do the cube for the number there, 3 times 3 times 3. And in this case, we're going to divide by 27. Then we're actually going to take the 4th root there afterwards, right, to clear it. And if we do all that good stuff there, that's going to take us 2 to the minus 32 divided by 27. And then the 4th root, which will get us essentially here, do a little scientific notation, 5.2 times 10 to the minus 9 molar. If you're not sure how to do the 4th root, if you actually have a button on your calculator that looks like maybe something like this, then you would hit 4 in this case, then that button. If you don't have that button and you got like a caret or something like that, or a times 10 to the x or something like that, you could do 1 divided by 4 in parentheses, and that will do the 4th root for you. 1 divided by 2 would do the square root. 1 divided by 3 would do the cube root. If you could do that, if you could do it that way as well. So those are a couple buttons that you typically have. That gives us our molar solubility here of the aluminum hydroxide. Again, that is what S equals. In this case, we see that aluminum actually equals S, which means that its concentration would be 5.2 times 10 to the minus 9 molar. And in this particular case, if we actually wanted hydroxide, although it didn't ask for it, it is actually 3S. So here, if we wanted the hydroxide concentration at equilibrium, we would have to multiply that value we just got by 3 and get us our proper hydroxide concentration, which would be times 3. something like 1.57 times 10 to the minus 8 molar. First off, any questions on that? By the way, since I have the hydroxide concentration, I could actually calculate the pOH for this solution minus the log of 1.57 times 10 to the minus 8. Gives me a pOH in this case is 7.81, and our pH then would be 14 minus that. And actually our pH of this solution, even though it's got a little hydroxide in it, 6.19 is where it's sitting actually at this point. Yeah. Any questions on that there? So again, there's a lot of things that you can sometimes get from KSP, and one of these things, as we'll talk about a little bit later, is you can actually calculate the pH of the solution if you have something like hydroxide or obviously H plus or something like that. Any questions on that there? Clearly in this question, it just asked for aluminum. The others were a free add-on for today. Yeah, any questions on that? Then let's talk about using actual KSP values to help us determine solubility. And there is a certain situation where you can use the KSP values directly to predict what substance would be more soluble than another. And so, for example, if we take silver iodide like it has here, and we take that guy and we break it apart into its ions, that's a silver and an iodide. We take copper 1 iodide and break it apart here into its ions here. And lastly, if we take our calcium sulfate, break it apart into calcium and sulfate in this case. We can use the KSP values directly to compare this, and the one reason we could do that is each of these guys basically break apart into 2 ions. So each of these guys break apart into 2 ions. Each of these guys break apart into 2 ions, which basically means if you do the math for that, they're all going to be basically the square root. It's all going to come out the same math. So because they break apart into the same number of ions, you can actually use the KSP values to directly compare which one should be more soluble, which one should be least soluble. And it would be the same idea as K that we normally talk about, as we talked about here, solid on the left, aqueous on the right, which means if I have a large value of KSP, that's basically a large equilibrium constant, and a large value of K would mean I would mainly have products. So this guy would be more soluble, right? If I have a small value of KSP, that means small value of K, mainly reactants in this case. And that would mean that it would be less soluble, right? So if you have the ability to compare KSP values, and again, the only way you could do that is if whatever you're comparing breaks apart into the same number of ions, the larger the KSP value, the more soluble that guy is. The smaller the KSP value, the less soluble that is. So if we were to look up the values here, we would see that the calcium sulfate has the largest KSP value, and it would be the most soluble, while the silver iodide has the smaller KSP value and would be the least soluble of those three, obviously with the copper there in the middle of those two. Any questions about there? Now, what happens in a situation like this where we want to know about the solubility comparison of these guys here? When we look at copper 2 sulfide, and again, we break it apart, we're going to get a copper 2 ion and a sulfide ion. We look at silver sulfide. When that breaks apart, we get 2 silvers and a sulfide. And when we look at the bismuth example here and break that guy apart, we get a couple of bismuths here at 3 plus and 3 sulfides there. So in terms of ions, we have 2 ions here, we got 3 ions here, and we actually got like 5 ions happening here. So because these guys break apart into different numbers of ions, you actually cannot use the KSP values to correctly compare solubility, because truthfully, the math is much different in each of these, because some are square, some are cubed, and all that math. And just to illustrate that, if we did look up the KSP values for these three, what we would actually see is this guy here has the largest KSP value, and this guy here has the smallest. And what you would predict based off of KSP is that this guy should be the most soluble, and this guy should be the least soluble if you use the KSP to do that. But because they do not break apart into the same number of ions, you actually have to do the calculation like we did in the previous examples to figure out what is the molar solubility of each of these. So you'd have to do an ice table and actually go through the calculations. And if you actually do go through the calculations, you would actually see it is the bismuth one in this example that actually is the most soluble. And it's actually the copper is actually the least soluble. So in this case, you cannot use the KSP to compare. You actually have to do the calculation, and you would see that the correct solubility there. Any questions on that there? So let's talk about some things that can affect the solubility of something. So as I mentioned before, sometimes when we're taught solubility rules, we're taught them as like they are always 100%, always going to be the case. But there are a lot of factors that come into play as to, again, like I said, whether or not you'll actually see something precipitate out or not precipitate out. And one of the things that can affect solubility is the presence of a common ion. Now, the presence of a common ion will decrease the solubility of it. And if we just think logically about KSP sort of equations, again, solids on the left, aqueous ions are on the right, which means if you have a common ion present, it would be like you added more products, right? And if you added more products, Le Chatelier's principle would say the equilibrium would shift away from the side you added it to, and it will actually keep that solid together, and you actually will not break it apart as much, and it will actually decrease the solubility. So if we take a look at silver bromide, for example, in pure water, we take our silver bromide and break it apart into our silver ion and our bromide ion here. And again, we could write our KSP, which would be in this case our silver times our bromide. And that's going to equal 7.7 times 10 to the minus 13. Now, if we run through our ice table here, we have 0 and 0, our change plus S at equilibrium, S and S. This is going to go into our KSP, which basically will give us S squared is equal to 7.7 times 10 to the minus 13, a little square root of both sides here, going to give us a molar solubility here of we'll call it 8.8 times 10 to the minus 7 as its molar solubility. Now, what would be the solubility of silver bromide in a solution that also contains sodium bromide? So what's going to happen in this situation is for B, this was A, obviously, here in B, we will still have our same equilibrium set up. But instead of being in water, we do have some sodium bromide, which is a salt, and it will break apart into a sodium ion and a bromide ion. And as you could probably guess, it is the bromide ion here that is our common ion that we're going to have with our equilibrium. And it is 0.001, which means how it affects the ice table is this would be 0, but we would have an initial concentration here of bromide, and that's being supplied by this guy, the sodium bromide is where that initial concentration comes from. The rest of the ice table will be similar, plus S and plus S. That means at equilibrium, S 0.001 plus S. Just like we normally do, right? We'll put this into our KSP expression. It's the same KSP expression that we used previously. So putting that in there gives us S 0.001 plus S equals 7.7 times 10 to the minus 13. One of the nice things about KSP is they are very small, usually equilibrium constants, which means just like normal, why not assume in this case S is equal to 0? So we can make an assumption like we did with the X's, and it will probably be in good shape here. In this case, just like we do with X's, we are only going to get rid of an S we're adding it to or something like that. So it's just going to be that S. That would get us S times 0.001 equals 7.7 times 10 to the minus 13. Gonna divide that to the other side. That's gonna give us a molar solubility of 7.7 times 10 to the minus 10 molar. You can also check it here by dividing by 0.001, times it by 100. But in most cases here, you're going to be in good shape because it is a very small K value, and a check is good, by the way, here. But what we do see is without the common ion present, we have a molar solubility for silver bromide of basically times 10 to the minus 7, which is a much larger number than we see when we do have the common ion present. It is 10 to the minus 10. That's a lot less soluble. And again, the idea here is we're basically adding this guy. That's going to cause the equilibrium to shift away. And again, going to keep it together and decrease the solubility. Any question? All that there. All right, so why don't you try one here? The KSP of silver chromate is 9 times 10 to the minus 12. What would be the solubility of this compound in a solution solubility rules? We know this is going to be our solid here. And again, we want to break this apart correctly. So we will have 2 silvers, as that 2 will come to the front, and chromate is minus 2, which is why there's only one of them there. Our KSP expression in this case would be the silver concentration. We do again need to square it because of the coefficient, and our chromate in this particular case. And obviously that equals, we got there 9 times 10 to the minus 12. All right, so initially here, we're going to have 0 for our silver. This is, though, in a solution of potassium chromate, and potassium chromate is K2CrO4, and that is a salt because potassium is soluble in everything. That will break apart into 2 potassiums and a chromate. And since it is a 1-to-1 relationship between these two, the concentration is basically the same here. So this will give us our 0.1 molar. Again, the 0.1 molar coming from our potassium chromate, basically supplying that. Here, then the change is going to be plus 2s in this case, and plus s. We will end up with then 2s 0.1 plus s. Any questions on that there? Putting that into our equation there, 2s, and I do need to square it, and then our chromate 0.1 plus s is going to equal our KSP of 9 times 10 to the minus 12. Once again, we could assume x is equal to 0. And again, it is going to be just the x like we, in this case, usually will be plussing from something. That's going to give us here, and I'm going to kind of clean this up here. That's going to give us a 4s squared. Again, remember, you do have to square the 2 as well. We got 0.1 gives us 9.0 times 10 to the minus 12. however you want to do it. I'll do 0.1 times 4 gets me 0.4 s squared is 9 times 10 to the minus 12. I then could take this to the other side and then afterwards square root it. So we're going to divide 9 to the minus 12 divided by 0.4 and then a little square root. Gonna get us here, I think, a molar solubility of 4.7 times 10 to the minus 6. And again, this would be the solubility here of our silver chromate. If we wanted grams per liter, we would then get the molar mass of it and use that. By the way, if I wanted the silver's concentration at equilibrium, it is 2s, so I would need to take that number and multiply it by 2. Just like if I wanted chromates at equilibrium, I need to take 0.1 plus that, which would actually still be 0.1 very much, but that would be how you would get those guys if you needed to.